In the last video, we introduced the concept of landmarks, and now we can evaluate the true position of the robot using those landmarks. In this video, I would like to assign a probability or weight to each particle, and this weight will represent how close, how probable a specific particle is to the robot's true position. So, what we have here is the true position of the robot, and the robot has X and Y. This is the true position of the robot, and let's assign it XR and YR, X robot and Y robot. And also, we have many particles. If you remember, each particle represents a guess regarding the true state of the robot. Now, since I spread out the particles, I know the specific state of each particle, and this is very important. I set the particles, hence I know where each particle is. Now, in this example, I will focus on this particle over here. Now, you need to do the process that I'm doing for this particle for each one of the particles. So this particle, let's call it Pi, which is the ith particle, also has an X value and a Y value, also has an X value and a Y value. Let's call them Xi and Yi. Since I know where this particle is, and since I know where each of the landmark is, I can compute the distance between that particle and each one of the landmarks. In other words, I can get a z, or a sense function, regarding this specific particle. So what we have is, this is di1, which means the distance from the ith particle to landmark 1. This will be di2, and this will be di3. So each particle has a z function or a z vector containing three different measurements or three different computations regarding the distance from each particle to each one of the landmarks. If in case...
each one of the landmarks.
Okay. So each particle has a state vector. So each particle has... Okay. So each particle has a z vector, and the z vector is basically list of all the...
A list.
And so each particle has a z vector, sense vector, and that sense vector is basically a list of all the differences between each particle and the three landmarks. And the size of the vector is the number of landmarks by 1. In our case, since we have 3 landmarks, the size of the vector will be 3 by 1. And again, you have to repeat this process for each one of the particles. Basically, this vector is what you would have gotten if the robot position was exactly at Pi. Again, this is very important. Each particle is a guess. So let's say that I'm in that position at Pi. What do I need to get from the sensors? Zi is very easy to compute if you know the x and y values of each particle and you know the x, y values of each landmark. This is a very easy computation. But I have another z vector, and this vector contains the true measurements of all the landmarks from the real position of the robot. In other words, I get D1, D2, and D3. This is the real observations that I'm getting from the sensors. Now, all I need to do is to come up with a function that assigns a high probability or high weight to two vectors that are similar, and will assign a low probability or a low weight to two vectors that are further apart. How do we do that? I will give you 2 methods to do it. This is the first method, very simple. Basically, what I'm looking at is the difference between the measurement between the robot and landmark 1 and the hypothetical distance between the particle and landmark 1. For example, if our true measurement from the sensor give me the following, z equals 60, 32, 48, which means that we measured 60 meters between the robot and landmark 1, 32 meters between the robot and landmark 2, and 48 meters between the robot and landmark 3. And what we have is Zi, the computed distances between the ith particle and all the landmarks, for example, is 50, 81, and 53. So the weight function should be 1 divided by 10 plus 49 plus 5 plus epsilon. Why? Because the difference between 60 and 50 is 10, the difference between 32 and 81 is 49, and the difference between 48 and 53 is 5. Now, why do we need the epsilon? In the rare case where both vectors are identical, I don't want to divide by 0. Therefore, I add a tiny epsilon. This is a very simple method and it works. But if I have a knowledge regarding the true inherent nature of the sensor, I can be smarter. Let me explain what I mean. So what do we know? We have the true robot's position and we have the ith particle. Now, let's assume that the distance function between the robot and each landmark contains a Gaussian noise. Again, I don't have to be restricted to Gaussian noise since I'm in particle filters, and particle filters by their nature are not restricted to Gaussian anything. But it is a very plausible assumption since most noise in nature is Gaussian. So, what do I mean? Let's say that the distance, the true distance between the robot and LM2 is 60 meters. When I measure the distance using my sensor between LM2 and the robot, the measurements, the observations will be normally distributed around 60. Let me tell you what I mean. So I might get 58 and I might get 62 and I might get 65, etc., etc. So the Gaussian noise model basically means that the probability to get 58 is equal to the probability to get 62, and the probability to get 65 is much higher than the probability to get 70. Okay? And again, you don't have to assume it, but this is a very plausible assumption. Now, what I'm having is the following. I know that the computed distance between the ith particle and landmark 2 is not 60. I know that the computed distance is 30, for example. And again, for each particle, I assume that my true position is the particle's position. And now the question becomes, how likely is it for the true distance of 30 with a known standard deviation to get a measurement, an observation of 60? This is very important because the true observation that we got from the sensor is 60. And there is no question about it. This is what we got from the sensor. But what do I need to ask is, assuming that the true distance is 30, how likely is it for a non-standard deviation to get an observation of 60? How do we do it? Using the Gaussian PDF. Watch. We are already familiar with this equation. What do we need? We need sigma, the standard deviation. And how do we get the standard deviation? From the datasheet. The sensor's datasheet will tell us what is the standard deviation of this sensor. What is mu? Mu is the computed distance from the ith particle to the landmark. In our example, it will be 30 because this is what we computed. What is x? X means the true observation, the true value that we got from the sensor. So I can compute it and I will get P, the probability of LM2. okay, the probability of LM2 for the ith particle. And I will need to do it for LM1 and LM3. And I need to multiply those probabilities because those are independent probabilities. So the probability or weight of each particle is basically the multiplication of those three elements. So again, let me emphasize what those elements are. I get a computed distance from the ith particle to the landmark. In our example, it will be di2 or 30. But again, I'm getting another true value from the sensor. And the sensor says, the measurement that we got is 60. So now I need to ask myself, how probable, giving a known standard deviation of the sensor, how probable is for a distance of 30 to get 60? And this will be a very tiny figure. And I need to multiply this tiny figure by the probability of di1 when we actually get d1. And I need to multiply it by, again, what happens with d3. So we end up with very small numbers, and therefore we need to normalize them. And we'll speak about it in the next video.